Good evening, Wangaratta. My name is Rick Tonello. I'm the Chief Astronomer at the Gravity Discovery Centre and Observatory all the way out here in Western Australia, and it's an absolute pleasure to be here tonight to talk to you about the lives of stars here on National Science Week 2021. I hope I'm coming through loud and clear. Please, oh good, I do have a message that I am coming through loud and clear, and that's fantastic. So it's good to see that we're going to get a whole bunch of people streaming on, oh, not streaming, but joining us online. And I'm hoping to impart upon you the wonder and just absolutely amazing lives of stars. Now, it's going to be a very abbreviated talk. It's only going to be about an hour long. Normally, if I was talking about this to students, it would take 2 hours long, and even then that's fairly abbreviated as well. So I'll try and keep things relatively simple yet mind-blowing and give you a better appreciation of the lives of stars. So if you just bear with me for a few moments. I was going to change screens, but I'll tell you a little bit about what I do at the Gravity Discovery Centre. So I'm the Chief Astronomer, and I'm responsible for the running of the observatory up there, up at Gingin. We've got beautiful dark skies. We're located about an hour's drive north of Perth, the Perth CBD, up in an area called Yale, near the small town of Gingin. And up there, because we've got beautiful dark skies, we've got a number of things that we have going on at the Gravity Discovery Centre precinct. Most notably is the Gravity Discovery Centre, which was established about 17 years ago to help people understand the true nature of gravity, i.e. Einsteinian gravity versus Newtonian gravity. I won't go into what the difference is at the moment, because that'll be another lecture. That'll be an hour long, and that's not what we're here to talk about. But from there, what we do is we explain how gravity works, but also with our observatory we teach astronomy and astrophysics not just to primary schools but also to secondary schools and tertiary students as well. So we have our astrotourism operation. We are the centre, well, no, I wouldn't say the centre, the astrotourism capital of Western Australia. We've got beautiful dark skies, great telescopes, fantastic staff. So if you wanted to ever, when this pandemic goes away and like to join us, come over for a visit, and it'll be great to show you the universe. So we have our astrotourism component where we have visitors on a Friday, Saturday, Sunday night. We also have our astronomy education component where not only do we have schools coming up to the observatory to experience the dark skies and big telescopes, etc., but we also travel out to schools and we take telescopes, so we bring the universe to you. We also have astronomical research going on site. That's thanks to the University of Western Australia and something called the Zadco Telescope, which is the largest optical telescope, non-military telescope, in Western Australia, and that does mainly high energy physics. And we also have our local Aboriginal connection as well. We do our famous local Aboriginal astronomy nights, where you can learn more about the Yonga people and their stories of creation and star lore. But we also aim to show off the local flora and fauna that surrounds the area, which is quite unique from that part of the world. Anyway, enough of me yammering on. I suggest I'll get my mug off the screen and actually get to the good bits where we start talking about stars. If anyone has any questions, please think them up, and then I'll answer a whole bunch of questions at the end. So here we go. So get rid of this. I have to start my talk up, so just bear with me for a second. It's a bit of a schmozzle here on my screen at the moment here. Here we go, and hit the play button. Hope this works. I'll just double check my other screen that I've got running. It should pop up, and if it doesn't, then I'm in trouble, but that's okay. I'll figure something out. Here we go. Now, the lives of stars. This is essentially it's a crash course on stellar evolution, and of course presented by yours truly. Okay, it'll eventually change screen. There we go. Alrighty, fantastic. So here is a picture of our Milky Way Galaxy. Now this is our home in the universe. It was first described correctly by a philosopher, a fellow called Immanuel Kant, around the early 1800s. He described these small spiral nebulae, as astronomers of the day described them, he suggested that these may be full of numberless stars, and he called them island universes. And of course that is what our focus will be on tonight, is the actual stars themselves. But galaxies themselves are huge aggregations of stars and gas and dust and planets. And this picture here shows us quite a lot of detail just for our Milky Way galaxy alone. Our Milky Way galaxy, just as a brief description, contains anywhere between 200 billion to 400 billion stars, and that's billion with the B. Now, to give you an idea of the sheer scale of just even the number 1 billion, if you were to count that, counting a number every second, it would take you 31,710 years of counting a number every second to reach. Oh, sorry, I go back. So no, that's a trillion. To count to the number 1 billion, I overcounted there. Counting a number every second will take you 31 years and 9 months. It's a big difference between 31,000 years. So 31 years and 9 months, it will take you counting a number every second to reach the 1 billion. So the Milky Way volume of stars is quite numerous, to say the least. The structure of our Milky Way galaxy is very, very similar to two fried eggs, where you imagine, the yolk and the white part, and one fried egg is upside down, one fried egg is the right way up, and you slap them together. And the central nucleus of the galaxy, I'll see if I can change screen, here we go. The central yolk part of our Milky Way galaxy is found here and down here. And the white part, which represents the disk of the galaxy, stretches out either side of it along here. Now what we can see is these vast dark gaps. These are huge collections or large clouds of gas and dust known as molecular hydrogen. Now these clouds of gas and dust, we'll explain more about it later on as the lecture goes on, but they are actually blocking our view in towards galactic central point. So they're obscuring our view optically, but with wavelengths such as infrared, radio, and some others, we can actually pierce through that gas and dust that obscures our optical view into the heart of our Milky Way galaxy, where, by the way, we've found a supermassive black hole at the center, which is approximately in the size of about, can't remember, 4.5 million times the mass of our sun. I'm looking at my other screen and this doesn't appear to be popping up, so I'm just going to be doing something else to rectify the situation. So I do apologize for any technical hitch here. Let me turn that on. There we go. And let me start that again, because you're probably just seeing me talking to the screen. Hang on a minute. I apologize for this. I'm using a new platform. Okay, so let's get to the part where it actually talks about, here we go. And there we are. So now you probably see what I'm talking about with the picture of the Milky Way galaxy here. So getting back to the fried egg analogy, there's one part of the, oops, this screen here. Too many screens. I've got like 5 screens going at once. It's ridiculous. So we have one yolk here, one yolk under here. There's the white part of the egg stretching out, and of course there's those dark clouds that I was describing earlier. That's better. I can see it coming on my other screen now. Anyway, so the ancient astronomers from all civilizations used to regard the stars with awe and wonder. And I want to, rather than talk about the Greek Greco-Roman constellations, I want to sort of highlight a little bit of local star lore. And the next picture I'm going to show you is another variation of the picture of the Milky Way galaxy I've taken here, except I took this photo out at a place called Lake Ballard, which, if anyone is familiar with their Western Australian geography, it's just located north of Kalgoorlie. There's a small town called Menzies, and then from Menzies you travel another 52 kilometers to the northeast in the middle of nowhere, and there's a lake called Lake Ballard, and it's a large salt lake, and on that salt lake is an art installation done by famous British sculptor Antony Gormley. He's produced all these wonderful statues that he scattered across the lakeside. And this is a fitting foreground to show off the Milky Way. Now, the stories that I'm telling it from, the perspective I'm telling it from, is from the Yonga people. That's the traditional caretakers of the southwest of Western Australia. So when they looked up at the stars, they saw 2 of their spirit animals. By the way, I just want to add a footnote. I've actually been given permission by a Wajak Noongar elder to tell these and show these to you. So I feel very, very fortunate in the ability to do that. And it's unfortunately there are a number of people out there who don't give that recognition or seek that permission, which it's a bit disappointing. But I mean, you know, they're stories that need to be shared, but to be done in the proper way. So getting on to the next slide here, this is two of their spirit animals here. Waich, the emu. Of course, the emu is depicted not just in Yonga culture and star lore, but also a whole bunch of other different mobs across Australia. They see that definite shape of the emu. So starting up here with this large cloud of gas and dust called the coal sack, following the neck down, the body arching across and actually disappearing behind the horizon, and all the way back again. Astride on the back of the emu is another one of the Yonga constellations known as Yonga the Kangaroo. And of course the head of the kangaroo is represented by the Southern Cross. There we are, there's the Southern Cross, there's the two ears of Yonga, the backbone of Yonga the Kangaroo, the tail, which is formed out of the constellation of Scorpius, its large foot, and of course the two pointer stars, which represent the two front paws of the animal. So this is what we see in wintertime, around sort of autumn through to early spring, in different orientations because of the rotation of the Earth around the Sun. I've got another one here. This is coming up in summertime, and this is a very famous constellation known as Orion the Hunter. We have the three stars of Orion's belt. We have his sword, his ankle. Oops, sorry, let me change screens. Three stars of his belt, his sword, his ankle, a star called Rigel, a red supergiant star called Betelgeuse, which represents his armpit, another star called Bellatrix, that represents his shoulder, and there is his shield. Now this is the Greco-Roman perspective. What I'm going to show you now is the Yonga perspective. The Yonga perspective didn't see a hunter or warrior figure. Some Aboriginal mobs do. They see it as a hunter or a warrior figure, but the Yonga people saw it as an echidna called Yingan. And I'll show you now what Yingan looks like. So starting from this part here, that's the snout of the echidna. There's the echidna's little face there. Arching all the way along here is the back of the echidna. There's the little tail, and then all the way across back to the face. But this is what it looks like. There we are. So there's Yingan the echidna, and this is what they saw. And all the animals that is depicted in the night sky for Yonga star lore are all facing south. And they all have their own stories, but it's not my place to tell those stories. But getting away from the actual constellations and star lore, let's talk about the stars themselves. Now, of course, this happens to be our sun. This is our sun. Now, our sun, don't forget, is a star. And to quote from the late great Carl Sagan, he said that stars are suns, but very far away. And our sun is a star, but close up. So our sun is actually considered to be a yellow dwarf star. It's actually small in size when compared to other stars, and we'll talk more about that in a moment. But stars of low mass like our sun, around 1 solar mass, and we talk about our sun being 1 solar mass because it is the closest star we can study in great detail. It is only 150 million kilometers away from planet Earth. So we can really see, we can study this thing in fantastic detail, and how it changes. It's very dynamic. Its surface changes. It goes through an 11-year cycle because of the magnetic field lines becoming entangled through something called differential rotation, where the speed of the rotation of our sun is about 25 days across the equator, but then it varies as much as 35 to 37 days up around the pole. Again, we won't get bogged into too much of that detail, but stars are natural thermonuclear reactors. Now, we're trying to replicate that down here on Earth to solve all our energy problems, to get away from nuclear fission reactors, where we split the atom and harness the energy from that. Also trying to get away from fossil fuels. Now, to harness the power of a star here on Earth is proving to be challenging, but we are making small incremental steps into actually harnessing the power of a star here on Earth. Now, to do that, you have to replicate the pressures and temperatures experienced inside a star, and that's quite challenging to say the least. So the diagram I'm about to show you next is a basic diagram of how our sun produces its energy through thermonuclear fusion. It's called the proton-proton chain reaction, and it's mainly found in low stars. High mass stars go through a different reaction called the CNO cycle, or the carbon-nitrogen-oxygen cycle. We won't delve into that. We'll just talk about this one here. So what we have is we have the most abundant element in the universe, which is known as hydrogen. There's hydrogen there. Now, hydrogen is made up, if anyone can remember back to their high school science days, the hydrogen atom is made up of one proton and one electron. Now, a proton, an electron, a proton is a positively charged particle, and an electron is a negatively charged particle. Now, normally atoms tend to repel away from one another. They get close by and then they bounce away. It's like getting two magnets and bringing their like poles together. You feel that electromagnetic repulsion. It's the same with atoms. They get close to one another, but then they repel away. Now, in the core of a star, where temperatures and pressures are extreme, I mean really, really extreme, the atoms overcome their natural repulsion, and they are literally slammed together. They cannot get out of each other's way fast enough, and they slam together, and when they do, they engage one of the four fundamental forces of the universe, known as the strong nuclear force. So the strong nuclear force is responsible for holding everything together. Without the strong nuclear force, stars wouldn't exist, planets wouldn't exist, people wouldn't exist, cars, cats, dogs, everything, anything that has an atomic structure greater than hydrogen would not exist. So think of the strong nuclear force's short-range hooks that latch together when put under great pressure and great temperature. They overcome that natural repulsion and bind together. So when we get two hydrogen atoms here bumping together, they overcome their natural repulsion and they change to a heavier version of hydrogen known as deuterium. Deuterium basically has a proton, an electron, and a neutron. Proton has positive charge, electron has negative charge, a neutron has no charge. Okay, so the hydrogen atom here has a proton, an electron, proton, electron. Now the amount of protons has to equal the amount of electrons, or the amount of electrons has to equal the amount of protons. But so we've got a proton here, electron, neutron. Where's the other electron gone to? There it is there. But it's changed its charge. It's gone from being a negatively charged to a positively charged particle. Now, why that happens, I'm not a nuclear physicist, but just the same, this is now transformed into something called a positron. So it's an electron, but with a positive charge. Another thing to call this is antimatter. Yes, for all you Trekkies out there, antimatter is real. When you have a positron meeting up with an electron, they annihilate in a flash of gamma ray radiation. And this is why stars shine. It is through that reaction there that the star produces energy. We also have another little particle called a neutrino that goes flying off. Now, neutrinos are very, very, very small, and they don't interact with anything. Now, I'm not sure if anyone remembers that god-awful movie called 2012. It was a disaster movie put out in 2012, stating that the Mayan calendar was, predicting the end of the world, and then some scientists in India saw the effects of neutrinos that were suddenly decided to interact with the core of the Earth and cause all sorts of core destabilization, and mayhem and destruction ensued. The knowledge that I have, seeing that happen, was eye-rolling and a facepalm moment. It's like, that's not how it works. Very bad science there. So after 4.5 billion years of producing neutrinos, all of a sudden now they start to affect the core of the Earth? I don't think so. But anyway, never let science get in the way of a very bad story, and I'm putting it down to 2 hours of my life I'll never get back. But anyway, that's another thing. But neutrinos were supposed to interact with the core of the Earth, but they don't. They're too small. In fact, we've got neutrinos passing through us right now, about the size of your thumbnail, the area of your thumbnail. You've got at least, I think the last count was about 10 billion neutrinos passing through you every second. And you don't feel a thing. So neutrinos are inherently small and they don't interact with matter. So there's nothing not to worry about. Anyway, back on with our why stars shine. So we got this gamma ray photon which causes the star to shine. Later we have deuterium meeting up with another hydrogen atom to produce helium. Helium, of course, you find it in party balloons, you suck it back and you can talk with a squeaky voice and you're the life of the party. But again, more gamma rays are emitted, and it's that gamma ray production that gives our sun its energy. Now, everyone should be familiar with this picture, this diagram. This is, of course, the periodic table of elements. Now, this is a chart that charts out all the naturally occurring chemical elements. Everything from the most basic element, hydrogen, to helium, and lithium and beryllium and boron and carbon, nitrogen, oxygen, fluorine, neon, all the way up to element number 92, uranium. That is the, of course, the heaviest naturally occurring element we find in nature. Now, we see from that previous chart that we start squeezing hydrogen together to form helium over here. So we've created a new atom in the core of a star. So the core of a star is a crucible for where heavier elements, chemical elements, are produced inside the core of a star. Now, for a star, especially a high mass star, the reaction stops at iron. Now, iron's a tricky little thing. You see, nuclear fusion stops at iron, and elements lighter than iron release energy through nuclear fusion, which is what I just described. But elements heavier than iron release energy through nuclear fission, where the atom is split, like the nuclear reactors we have today. Now, iron has the lowest mass per nucleon, so it cannot release energy through fusion or fission. And we're going to talk more about iron when we talk about high mass stars. But a lot of these chemical elements are very, very familiar to us, especially ones like carbon, nitrogen, oxygen, fluorine, magnesium, sodium, potassium, iron. What else we got? Chlorine. Even smaller producers like gold. These are very familiar because this is stuff that we're made of. We are made of these naturally occurring chemical elements. So let's have a look at the human body. And of course this is titled, What is Dave Made Of? You could insert your favorite name here. And of course when we look at the quantities, we see there's quite a lot of oxygen, quite a lot of carbon, hydrogen as well, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, and they go more and more and more on. And eventually we start coming to some pretty weird stuff like titanium. It says here we got 20 milligrams naturally, but if anyone's had a hip replacement, I'm sure you have a lot more titanium in you now. So if we can keep going down, and we actually start to come to some quite weird chemical elements like yttrium and gold, and eventually we start getting into like thorium and uranium, radioactive stuff, and tungsten and beryllium. So we are made, the human body is made up of 59 naturally occurring chemical elements in various quantities. There's quite a lot of oxygen and hydrogen because they're bonded together to form water, which you're made of about 70% of. There is a lot of carbon because that's what your skin and your muscles and your guts and your eyeballs are made of. There's calcium in your bones and your teeth. There's in your bloodstream, there's potassium and sulfur and sodium and chlorine and magnesium and iron and fluorine and zinc. And a whole bunch of other things that make up you. And when they're constructed or put together in complex molecular chains, you form a molecular machine known as the human body. So give atoms a few billion years and they'll start to form complex molecular chains and eventually life. So another way to put it is every atom in your body came from a star that exploded. So again, to draw upon from my hero Carl Sagan, we are made of star stuff. Through every atom in your body that came from a star that exploded. You are a product of 13.798 billion years of cosmic evolution that has prototyped all these elements in the cores of stars that have subsequently blown up and seeded the greater universe and galaxies with these materials, the stuff necessary for life. Alrighty, let's explain how stars are born. So, eventually when my screen changes, here we are. I'll begin back to a picture of our Milky Way Galaxy. Now, just by looking at this picture, we see vast reservoirs of the material of building stars. And that vast reservoir, of course, I'm referring to is these vast molecular clouds that interrupt our view in towards the center of the Milky Way Galaxy. So these contain vast amounts of hydrogen. I think somewhere in the order of about 70% hydrogen, 28% helium, and the other 2% is everything else you find on the periodic table. Now they're cold and dark because they're quite well spread out, and also because space is cold. Things don't tend to heat up unless they're close together, because temperature is just essentially measuring the jiggling of atoms. The slower the jiggling of the atom, the colder it is. The faster, the hotter it is. So, like I said, these are vast clouds of cold, dark gas and dust that, I wouldn't say pollute, but populate our Milky Way Galaxy. Now, what happens is gravity then collapses these areas of gas and dust into smaller areas known as H2 regions or nebulae. So this little one here, but there's another particular one I want to zoom in over here. That's the one right there. So we're going to have a look at that particular H2 region. H2 is meaning it's ionized hydrogen. Hydrogen that is releasing photons so we can actually see its presence. It is glowing because of energy within that nebula through stars that are being born. So let's zoom up. Here we are. This is a picture of something called the Eagle Nebula, or Messier 16, named after Charles Messier, who was an avid astronomer, and he created a catalogue of about 100 objects, and this happens to be the 16th one in his catalogue. And what we see here, this is a picture I took from the Gravity Discovery Center Observatory late one night when all our visitors have gone, and what it reveals to us is this vast network of hydrogen. So this is the H2 region I'm referring to. This is hydrogen here, and it's glowing. It is ionized by the stars that are in the center. You see, the stars are producing vast amounts of ultraviolet radiation, and they're causing the surrounding gas and dust, or the gas, to glow, to ionize, throwing out photons of light so we can actually see it. But we can see in this little area here, we'll zoom up on that in a moment, but the gas and the dust isn't distributed evenly. It clumps together. Gravity and other forces, turbulent forces, push it together. So what we're going to do is we'll zoom in to a proper picture of the Eagle Nebula, and here it is there. And of course this is taken with different colors. This is known as the, I think it's the Hubble palette, where the various other ionized gases are highlighted via different colors. So what we're going to do is we see there's large, thick columns of gas and dust all along through here, and another thick globule there. This is almost like observing inside a hollowed out pumpkin. Yes, it is a three-dimensional structure, you must remember. So let's zoom in on this area right here. Now, of course, everyone will recognize this picture when I show it. This is of course, the pillars of creation. Now, the pillars of creation are vast columns of gas and dust where stars are born. Now, the Messier 16 and the Pillars of Creation are located about 5,700 light years away as the crow flies, and about the nebula itself is about 15 light years across. Now, the previous picture showed us that group of stars in the center, and this star is estimated to be approximately 5.5 million years old. So, getting back to these pillars here, these are vast structures in themselves. I mean, for example, the tall pillar on the left-hand side is approximately 1 light year long. Now, for those of you who don't know what a light year is a measurement of distance that astronomers use to measure the depths of the cosmos. And it's based upon the distance that light travels at the speed of light for 1 Earth year. Now, the velocity of light through the vacuum of space is very fast indeed. It is 299,792,458 meters per second precisely. Now, to put it another way, if you could travel at that velocity, you could circle the Earth 7.5 times in 1 second. So it's very fast indeed. But if you travel that in a straight line, you cover a distance of approximately 9.46 trillion kilometers. That's a big number to write out, to say the least. So instead of writing out 9.46 and a whole bunch of zeros, it's easier to write out 1 ly, 1 light year. It describes two things. It describes the distance, how far away the object is. It also describes how long the light has been traveling for from that target to reach you. Now, one thing I do like to tell our visitors that when they observe through our telescopes is, again, I quote Carl Sagan, where I say that telescopes are time machines. Because when you look through a telescope, you see things as they were, not as they are. You see, the further into the universe you observe, the further back in time you're observing. So if you wanted to look at, say, our moon is only 1.2 light seconds away. So when you observe it with your naked eye or through a telescope, you see the moon as it was 1.2 seconds ago. If you were to observe, say, the closest star to our sun, or closest stars, I should say, is the Alpha Centauri system, they lie about 4.3 light years away. So you see them as they were 4.3 years ago, so on and so forth. We like to show a galaxy that is 67 million light years away. It's a wonderful galaxy called NGC 1399, which lies at a distance of 67 million light years away. But to really drive it home, I like to tell our visitors, our clients, that the light left 1 million years before the dinosaurs were wiped out by the Cretaceous Tertiary impact that occurred 66 million years ago. So when the light left, dinosaurs were still walking around on the surface of planet Earth and would continue to do so for another million years. Anyway, I digress. So we notice that this is a very thick lump of gas and dust. And I want to turn our attention to the very, very top of the top of the top pillar. And we'll zoom in on that. And you'll notice there's these protruding finger-like structures. And what they are, those protruding finger-like structures are even denser areas, and they're called appropriately eggs, or evaporating gaseous globules. Now, the eggs, they're literally it's a cocoon that is protecting the inner workings from ionizing ultraviolet radiation, which is responsible for sort of blowing stuff away. Now, these dense areas are shielded by this evaporating gas globule, and inside could be the formation of something known as a protostar. And a protostar is the embryonic beginnings of a sun, a star. And to give you a sense of scale, the very, very tip of the arrow that I'm showing here, about half a pixel's worth. In fact, let's just call it a pixel, because I'm trying to imagine half a pixel. But a pixel's worth at the tip of the arrow would be about the size of our solar system, all the way out to the planet Neptune. So these are vast structures indeed. Now, I'm hoping this works. This is a simulation of how these clouds of gas and dust through gravity collapse and start to form new stars. So here we go. I'll try and not swear if it doesn't work. Oh, here we go. It's working. Hooray. So you'll notice the time scale at the top here. Of course, we're going through tens of thousands and eventually hundreds of thousands of years, and the gas and the dust is being manipulated by not just gravity, but also by strong internal stellar winds or ionization. And what we see is it tends to condense, and those bright areas in the center here are high concentrations of gas and dust. Now, pay particular attention to this little area here. We now start to see the formation of stars. There's one there, there's another one there, there's another one there. And it's through this, and more and more are being produced, more of these denser areas. Gravity starting to collapse the star. Oh, pay particular attention to this one taking off here. That has something called an accretion disk around it. That will probably go off to form planets. But gravity collapses the gas and dust to form protostars. As the protostar increases in mass, it increases its gravitational field, you could say, and draws in more material to increase its mass. And as it increases its mass, temperatures increase in the core. When it hits a critical temperature of about 8 million degrees Kelvin, or 8 million Kelvin, that is where nuclear fusion is initiated, where the atoms bash together, stick together through the strong nuclear force, and start to emit energy. Now, as we pull back, we now start to see a scattering of stars, and this is what's called an open cluster, sometimes referred to as a galactic cluster. Now, we can see a number of them through telescopes, even with your naked eye. The Seven Sisters, the Pleiades star cluster, is a famous open cluster. All those stars form together from the same cloud of gas and dust, but because each star has its own proper motion, the star cluster will eventually disperse after a few hundreds of millions of years. So eventually the Seven Sisters will disperse, just like another one called the Jewel Box, which is found just near the Southern Cross. So that's a very abbreviated way of how stars form, is through the collapsing cloud of gas and dust of an H2 region. Oh, I'm getting a call. I seem to have there we are. Let's try that one now. There we are. Let's try this. Hello. Okay, I'll sort it out. Okay, what do we got? We may have some technical issues here, folks. I will just see if I can do something here. What do we got? What do we got? What do we got? Okay. I think, no. Should be coming through loud and clear. This is very weird. Screen's blank. Can you speak louder? Okay. Okay, let's try this. I'm hoping, oh, here we go. I'm back on apparently. So let's get back on with the show. Okay. This should be coming up now. And apparently I need to talk up. I'm talking too softly. Here we go. So, as I stated before, stars are suns. So it should be coming back up, I'm hoping now. So on with the show. And I'm sure, here we go. Yes, fantastic. So, here is our sun. And this is the end product of that formation. So, this is what forms from that collapse of gravity. Also, through gravity, this is what forms through the collapse of that cloud of gas and dust, a star. This is our sun. Now, of course, like I said before, our sun is the closest star we can study in great detail. Here's a picture I took a couple of years ago of our sun, our local star, with a solar telescope that I possess. And we can see it's a very, very dynamic surface. But compared to our planet, our sun is quite large, even though it is classed as a yellow dwarf star. And just to give you a comparison to show you how small planet Earth is in relation to our sun, that is planet Earth, right there. That is our home. This little ball of blue and white and occasional brown, ball of water and silicates and a whole bunch of iron and stuff. So that's us. So a little bit more about our sun. It's about 4.6 billion years old. Actually, more about 4.5 billion years old. It is about 1.4 million kilometers across, which means you could line up the Earth about 110 times. It is classified as a G2 main sequence star. We'll talk about that in a moment. Well, the special chart I want to show you has a surface temperature of about 5,500 Kelvin, core temperature of about 15.5 million Kelvin. At that sort of temperature range, you might as well call it degrees Celsius. Distance to Earth is approximately 150 million kilometers, or what astronomers like to call 1 astronomical unit. And its energy source is the proton-proton thermonuclear fusion reaction, which I explained earlier. But certainly our sun, when compared to other stars, is very small, hence the term dwarf. Now, let's have a look at some of the biggest stars we know of. Now, there's our sun right here. That's our sun. Then, of course, we have the brightest star in the sky, a star called Sirius. Following up from that is a star called Pollux, which is in the constellation of Gemini. Over here we have Arcturus, which is currently up at the moment if you have clear skies. It's found out towards the northwest. But then the biggest star that we know of so far is a red hypergiant star known as UY Scuti, which is found in the constellation of Scutum the Shield. This star is so painfully huge, it is so mind-numbingly huge, that where you could fit 1 million Earths inside our sun, you could fit about 2 billion of our suns into this one red hypergiant star, UY Scuti. So I'm hoping that would have blown away a few people. Every time I hear it, it certainly puts things into perspective for myself. So let's move on to one of the most famous star-forming regions that we know of. It's actually visible to the naked eye. It, of course, is the Great Orion Nebula. There it is there. Now this is of course found in the Sword of Orion, and it's easily visible with a pair of binoculars and certainly a small amateur telescope, and you can even see it as a small, faint, smudgy little star with your naked eye. But the Great Orion Nebula is a very productive stellar nursery. In fact, studies with the Hubble Space Telescope have shown us that there are some 700 protostars being formed right now in its realm. So 700 stars are in the process of formation. And this next picture here will show you something quite remarkable. I find it remarkable, actually. So we have the protostar here in the center, right there. And of course, there is no nuclear reactions going just yet. But what we're seeing here is the infrared or the thermal signature of that protostar. But then we see this dark, opaque disk surrounding it. This is what's known as an accretion disk or a protoplanetary disk. And as the name suggests, not only are we seeing the formation of a star, we're also seeing the formation of a solar system. Now, there are approximately, I think, about 170 protoplanetary disks around those 700, or some of those 700 protostars. So not only are we seeing the birth of stars, we're also seeing the construction of 170 solar systems, which is remarkable indeed. Now, stars, one of the most easiest features to discern is of course the color and their brightness. And of course we call color, we call it spectral type, and brightness, we call it its magnitude. So let's have a look at the color of stars, and they come in different colors. They come in deep blues, blue whites, whites, yellows, oranges, and reds. Now, despite what your bathroom taps have told you all your life, that blue is hot and that blue is cold and red is hot, it is the other way around for stars. You see, red is relatively cool and deep blue is excruciatingly hot. As we can see with this dark blue star, temperatures can kick up to at least 50,000 Kelvin, where at the other end of the spectrum, red stars can drop as low as 2,500 Kelvin. Now, the reason for this is something called blackbody radiation. Now, blackbody radiation is reasonably easy to explain. Again, I won't go into the exact mechanics of it, but having a look at this next diagram here gives us an appreciation of how blackbody radiation works. So let's do a thought experiment. Imagine you're in a completely pitch black room, and in front of you is a desk, and on that desk is an iron bar. You feel around, you find the iron bar, it's cold to the touch. So what you do is you pick it up and you hold it in your hands for about 10 minutes. What you're doing now is transferring your body heat into the iron bar. After about 10 minutes of holding onto this iron bar and transferring your body heat into it, you release it and stare intently at the iron bar. And you can't see a damn thing. That's because the human eye is not that good at picking up low, long wavelengths of energy. Now, the low wavelength of energy I'm talking about is, of course, infrared. If our eyes were more sensitive to those frequencies, we would see it glowing where you put your hand on it. Okay, so let's ramp up the experiment a bit and put an electrode either side of the iron bar, either end of the iron bar, and have electricity flowing through it, and you have a current regulator. So you click it up a couple of notches. Electricity starts to flow through the iron bar, and it starts to glow a dull red color, similar to that area there on the iron bar here. So what's happening is there's more energy in the system, the energy gets re-radiated out at a shorter wavelength and it's brighter, so we can start to see it. So then it's red color. So we click it up a couple of notches and allow more current to flow through. More current, more energy, the shorter wavelength that gets re-radiated out, it turns orange, it's brighter. We click it up a few more notches. More energy flowing through, shorter wavelength that gets re-radiated out, yellow. We click it up a few more notches. It is intensely bright, and that happens to fall around here, 6,000 K. We don't actually see green stars, but we see white stars. So it is so intensely bright, short wavelength coming out of this lot of energy in the iron bar, and we see it brighter, more energy, shorter wavelength. And then eventually we just grab a handful and turn the current regulator all the way up, and you can't even be in the same room as it because it's producing ultraviolet radiation. It'll give you sunburn, and it's so intensely bright you can't even look at it. So that is blue. So there's something called Wien's law that states that the more energy produced in the system, the shorter the wavelength gets re-emitted from that body. So low energy stars, which is around 4,500 K, which is, say, close to our red star, peaks in the red, orange, 6,000 K, which would be white, 7,500 K, which is blue, extremely hot. So blue stars are extremely hot, extremely energetic. Red stars, low energy, low temperature. That is why red is cool and blue is hot. But don't go having a warm shower and turning the blue tap on thinking you're going to get a warm shower, because you'll get a very rude shock. Anyway, based on the temperature of a star and its luminosity, how bright it is, two astronomers by the name of Enya Hertzbrung and Henry Norris Russell created a diagram. In fact, it wasn't Henry Norris Russell he did it, but it was actually one of his students, and that was Cecilia Payne, and a number of other of these famous Harvard computers, these women astronomers who were given the job of cataloging stars, making new discoveries just by data mining, essentially. So it was Cecilia Payne who classified these stars based on their spectral class. So it should be actually called the Hertzbrung-Payne diagram. Anyway, so let's have a look. This is the Hertzbrung-Russell diagram, or the HR diagram. So when you plot a star's luminosity along the vertical column here against its spectral class, you see we can put together quite a nifty little diagram of stars. And this tells us a lot of information. We can actually predict the future evolution of stars based on this diagram. So we have all the stable hydrogen-fusing stars up along this area called the main sequence, where stars spend about 70% of their time. We have more advanced, more evolved stars like orange subgiants and red giants. We have white supergiants, and of course we have the red supergiants, and then we have white dwarf stars. So getting back to our sun, which is found right there, there's the G part, and so it's a G2 class star with 1 luminosity. There we are, right there, that's us. Like I said, our sun is the closest star we can study in great detail. So we use that as a benchmark. And what we do to piece together the evolution and lives of stars is we don't just stare one star, because stars live, depending on their mass, for hundreds of millions, or tens of millions, hundreds of millions, and even billions of years. And of course you can't stay up all night and watch these things. You have to piece together the evolution of stars based on their brightness, their size, their temperature, their mass, and a whole bunch of other things, and if they've done anything weird in the interim. So let's have a look at the core of our sun. So what we have for our sun, and this is plotting the future evolution of our sun, we have the hydrogen envelope, which is the fuel tank, you could say, and there's no energy generation in that. There it is there. We have the hydrogen fusion layer, so that's the hydrogen burning shell where all the energy is generated there. And then when hydrogen squeezes together to form helium, where does the helium go? Well, I'm glad you asked. It precipitates down into the core to form this inert helium lump. and it just sits there doing absolutely nothing. So that, again, there is no energy generation coming out of that helium lump. So let's look at the evolution of our sun. Here we go. And we'll use the HR diagram to do so. So starting off here, there's our sun. Will spend 70% of its time in the main or along the main sequence as a stable hydrogen fusing star. In about 500 million to 1 billion years into the future, our sun will become slightly unstable because the helium core will start to increase in size. So, hang on a sec, something weird just happened there. Give me 2 seconds to check this out. There we are. So what will happen is our sun's core will be greatly enriched in helium, and it will increase in size. And this will push the layer, the fusion layer out closer. Now this will cause our sun to branch off the main sequence, and that branch off is how we determine the age of star clusters and other things called globular clusters, but that's a talk for another time. But this branch off point is around the 5 billion year mark of a star like our sun. So there we are. It'll branch off. It'll increase in or decrease in luminosity because the outer layers of the star are drifting away from the core. It's getting cooler. And it'll start increasing in brightness because star structures are sensitive to that kind of internal change. But as it increases in luminosity, it becomes a orange subgiant. So it's increased in size but decreased in temperature. So there's our orange subgiant. Inert helium core, hydrogen burning shell. Oops, sorry. There we are. Inert helium core, hydrogen burning shell. There we are. Subgiant right there. It will increase in size, as in its dimensions will get larger and larger and larger, and that will take it into the realm of being a red giant star. It'll peak to about here. In the interim, because we're still converting hydrogen to helium, the inert helium lump is increasing in mass, temperatures in the core are increasing as well, until we get to this very pointy bit here, which is known as the helium flash. That is where helium now starts to ignite and starts to form the heavy elements of carbon. But from here we notice the star again changes, goes back down to a yellow subgiant, but then the expansion continues and temperature drop continue up till it goes back to a red giant again. Now what does this mean for our solar system if our sun is going to swell up to be a red giant? Well, nothing good if you live on Mercury, Venus or Earth, because as it increases in size to become a subgiant, it's reckoned that Mercury will be swallowed up. It'll end up inside the sun. As it increases in size to become into its red gianthood, it'll certainly swallow up Venus. And there is a chance that, yes, you guessed it, the Earth and the Moon are toast as well. We'll actually end up inside our sun. But if we look at the structure here now, we have this inert carbon core, we have this thin shell of burning helium, and this thin shell of burning hydrogen. Now, the internal structure of the star then starts to become unstable. It starts to run out of fuel. And there's a whole series of contractions and expansions which literally puff the outer layers of the star outwards. You see, a star is in a state of hydrostatic equilibrium. You have nuclear reactions in the center forcing the star out. You have gravity collapsing the star in. However, these strong internal stellar winds, because our sun is a low-mass star, that puff the outer layers up to form something called a planetary nebula. And I'll show you a picture in that in just a moment. But what happens is the outer layers of our star get puffed out to expose the core of our star. And once that cloud of the outer shell of our star dissipates, what will be left is a white dwarf, the core of our sun. Now this is some 5 to 6 billion years into the future. Okay, so with the core exposed, all that will be left is a white dwarf star. There is no more nuclear reactions going on in the white dwarf star. It is pure radiant heat. It is a ball of carbon about the size of planet Earth. So it's very hot, small, and bright. Eventually, the white dwarf will cool down and it'll drop in temperature, eventually becoming yellow, orange, red, and then fading off to become a black dwarf stellar remnant. Now, astronomers and astrophysicists can say with great certainty, with great confidence, that there are currently in the universe right now, there are no black dwarf stellar remnants anywhere in the universe. And why is that? Because you need at least 100 billion years for white dwarf stars to cool down. And, well, the universe is only 13.798 billion years old. So it stands to reason that these white dwarf stars hadn't had enough time to cool down to a black dwarf stellar remnant. But what will be the end of our sun's life after 100 billion years? Well, what will happen is this large ball of carbon, because it's been put under great pressure and great temperature, as it cools down, the structure crystallizes. And of course, we all know what crystallized carbon is. It's a diamond. So at the end of our sun's life, in the far, far future, our sun will be a ball of crystallized carbon, a diamond the size of planet Earth. Here's a picture of a planetary nebula. This is the famous ring nebula, Messier 57, and what we see is the outer layers of the star that have been puffed out, and we see the progenitor star, the white dwarf, right there. So that is it, glowing with high temperatures, but it's very, very, very small. Okay. Now, this is the future of low-mass stars. So I'm going to skip over now to what happens the future of high-mass stars. And of course, when big stars, big massive stars die, their motto is live fast, die young, go out with a bang. And that, of course, is supernova. So a supernova is the spectacular self-destruction of a star, a high-mass star. And these things are pretty darn amazing. But here's the thing, we would not be here without supernovae. It is there in their fiery, explosive crucibles that they not only produce these heavy elements, but they scatter the elements out into the galaxy. So let's have a look. This picture here is of the gorgeous Eta Carinae Nebula. This nebula here is, of course, one of the showpieces of the southern sky. It's found not too far away from the Southern Cross, and you can actually see it with a pair of binoculars. It's pretty darn remarkable. And even what we can see just here is we see it's very, very red. This is the telltale sign of a lot of ionized hydrogen. So what we have here, there's a particular star in here that I want to show you, and it's that one right there, right next to something called the Keyhole Nebula. So there it is there. We're going to zoom in to that particular star there. Now this is the star of Eta Carinae. Eta Carinae is, well, it's got this weird double-lobed shape, this sort of peanut shape known as the Homunculus Nebula. And inside there's reckoned to be understood to be two stars. There is Eta Carinae A and Eta Carinae B. Eta Carinae B is the smaller one of the two, where it's estimated to weigh in anywhere between, I think, about 50 times to 80 times the mass of our sun. So this is a very, very large, massive star. The bigger one is anywhere, and I've read in various texts, it ranges from 100 times the mass of our sun to 200 times the mass of our sun. Sometimes even some texts quoted to be 250 times the mass of our sun. Now this is terrifyingly huge. This is a star that has had a very, very short, tumultuous life, and it suffered an outburst in the mid-1800s called the Great Eruption. And we see evidence here by these twin lobes where it has thrown off some of its outer material. Now this is a precursor for this star to go supernova. In fact, probably in this case, it might even turn into a hypernova. So supernova are some of the largest explosions in the universe. And it is caused by subsequent burning shells of elements that go down to hydrogen. I'll explain that in just a moment. But what's happening is this star... Oh, time's getting close. Thank you very much. So these stars are unstable. This star here is unstable. And in fact, since its eruption, it faded off to naked eye, beyond naked eye limits, but now has been steadily getting brighter since that eruption in the mid-1800s. Now, astronomers and astrophysicists have given this star somewhere within 10,000 years, this star is going to erupt. Given the fact that it's about 7.5 to 8,000 light years away, it might have already happened. So chances are this star has already exploded. Now, this is a very complex series of burnings till it reaches iron. Now remember back when I said iron cannot produce energy through fission or fusion? Well, it forms this inert iron lump, which is about the size of planet Earth. And iron is an energy-robbing element. So the equilibrium of the star, the nuclear reactions forcing the star out and gravity collapsing the star in, then becomes unbalanced. So with that inert helium core that is now robbing energy, that exertion of nuclear force holding the star up drops. And what happens is the core of the star collapses down at a very, very, very rapid rate. So the core essentially contracts in size from something about the size of Earth, about 12,000 kilometers across, down to something that's only about 100 kilometers across at about a quarter of the speed of light. Now, when it reaches that smaller state, it bounces. And as it bounces, it sends a shockwave permeating out through the star. But the star, being sensitive to any internal changes, the outer parts of the star come rushing in. And this outer rushing part of the star comes rushing in. The shockwave comes blasting out, and they meet headlong in this almost impassable collision. This collision then starts to produce other heavy elements. The shockwave then restarts again, rips through the star and blows it up. What we have here is a picture of a supernova that occurred back in 1987 called Supernova 1987A or SN 1987A. And of course, if we pay particular attention to the star that is highlighted by the arrow just down here, watch how luminous it gets. There it is. Now, the eruption of a star, the energy released by a supernova explosion the star can actually outshine an entire galaxy's worth of stars. In fact, this little GIF here, if it works, which maybe it will work, the energy released by a supernova is equal to the energy released by our sun over 9 billion years. That's a terrifying explosion. You certainly don't want to be around one of them. Sorry, I'm going to have to rush through all of this. Here we go. Let's try and move this forward a bit. Okay, seems to be stuck. Nevertheless, this is the delivery system of those these heavy elements through the cosmos, is through these explosions. And without supernova, we would not be here. So I will try and move this along. Something happens with these. I've lost my cursor. Okay, let's try this again. Okay. It seems to want to keep playing this over and over and over again. Okay. Okay, I seem to have lost everything. Okay. Let's see if I can quit this out. Anywho. No, even that's not working. Oh, there it is. I thought I saw it. My apologies for this, folks. Oh, there we are. Okay, I now have a frame of reference, and let us just alrighty. There we go. Alright, let's try this. My apologies for the technical hitch. Once it gets stuck on a there we are. Once it gets stuck on a GIF, it doesn't want to let go, which is a bit of a shame. So I'll just put my mug back up on the screen here. Nope. There we go, and get rid of that. There I am. So stars go through these very different changes depending on the mass. You see, a star's temperature, luminosity, and its lifespan are all dictated by its mass. The lower the mass, the longer the star lives. The higher the mass, the shorter the star lives. So these very large blue giant stars have got a very, very, very short life. Small red dwarf stars tend to live for extraordinary amounts of time. our sun, being like a happy medium in between, more erring to the smaller side, has a total lifespan of approximately 10 billion years. Red dwarf stars are estimated to live as long as 100 billion years. High mass stars can live as short as tens of millions of years. I would love to show you more about the end production of supernovas, such as neutron stars and pulsars and eventually black holes, but I'm not sure if we're running out of time. Perhaps that could be part 2 of our lecture sometime down in the future. But I'll tell you what, if there's any questions that we have, that'll be great to have, because I'd love to answer some questions before we have to finish up. So if we have any questions to answer, that'll be fantastic. Please tune in. That'd be great. And if not, then yeah. It's been great to be a part of the National Science Week for the Wangaratta Public Library. Hope everyone is staying safe over there. Hopefully the case numbers of COVID start to drop. It'll be really good and everyone can go about their business. So I take it we've got no questions. I'll just ask, the time's getting close. Yep. I'll just ask. There we go. Alrighty. If not, I'm sure there will be. I tell you what, you can always get onto the Gravity Discovery Centre Facebook page, and I'll put a link to this so people can watch it from our end of the world. And if you have any questions, you can always ask on that, and I will certainly do my best to answer them. But apart from that, we are starting to wind up on time, and yeah, I haven't heard anything from Mission Control at Wangaratta Public Library, so I'm going to sign off. So I thank everyone for tuning in tonight. I hope everyone stay well. Hope you learned a little bit more about the stars, and I hope you'll continue to do so. Not just from me, but from other things, reputable sources too. So on behalf of the Gravity Discovery Centre and Observatory all the way out here in Western Australia, thank you very much for taking part. Oh, there we go, Robert. Thank you, Robert Bruce. Great presentation. Could hear you all the way in Victoria and New South Wales border. Oh boy, I hope you built a wall. Did I say that? Whoops. Yeah, so take care, everyone. Thank you very much. Stay safe and have a great night. So thank you, and so long. Bye-bye.